We've talked about indefinite integrals quite a bit, but in this section and the next section, we're going to start to talk about definite integrals. So definite integrals help us answer another big question of calculus, which is how do you find the area under a curve? I can work with straight lines and create familiar geometric shapes, but if I'm working with something that has some sort of a curve and I want to find the area under that shape, it turns out it's a really tough question to answer. So we're going to start with an approximation. We're going to start with, okay, this question right now of finding area under a curve, it's too hard. So we'll start by approximating using shapes we already know, using rectangles to calculate this area. And then we're going to think about, okay, how could we take this approximation and make it better and better and better until we end up with something which is not an approximation anymore, something which is perfect. So the function we'll be working with in this example is f of x equals 9 minus x squared. We're going to graph this function over the interval 0 to 3. So let me just actually start right there. I'm going to graph this function. So I have 9 minus x squared. I should have a y-intercept of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 1, 2, 3 right here. And actually, let's actually spread it out a little bit more. 1, 2, 3 right here. So, okay, my parabola, it probably looks something like this. Something like this, let's say. Okay. Not perfect, but enough to at least give us an idea of what it looks like. So we want to estimate the area over this interval. So we want to estimate the area between our function and the x-axis. We're always talking about the area that's kind of caught between our function and the x-axis. So I would like to estimate what is this yellow shaded area. If I could know exactly what it is, that'd be great. But we're going to start with just an estimate here because it's a pretty tough question to answer. So we're going to do this using n equals 3 rectangles, and we're going to use the left endpoints for the height of each rectangle. So what we're going to do is we're working on this whole interval from 0 to 3, which is 3 units long. So we said, hey, we're going to use 3 rectangles here. So the first thing I'm going to find has a fancy name. It's called delta x. Delta x is simply, and let me write this out here, delta x is the width of each rectangle. So that is delta x, which the way I can find that is b minus a. So thinking about this, here's a, here's b minus a divided by n. So I'm just looking at how long is my interval and then dividing that by, well, how many pieces do I want to cut that up into? And that'll split the interval of 0 to 3 up into 3 equal pieces. So in this case, I have 3 minus 0 divided by 3. 3 over 3 gives me 1. And this works out nicely. That means each rectangle is going to have width 1. So I'm starting with this big long interval 0 to 3, and what I'm going to do now is I'm going to break it up into 3 smaller sections. Here's 0 to 1, here's 0 to 1, here is 1 to 2, and here's 2 to 3, and I know that each one of these smaller intervals has length 1. So I've taken this big interval and just broken it up into smaller pieces. And what I'm going to do with each of these pieces now is actually draw in rectangles. So I'm going to draw in rectangles using my function to help me determine how high each one of these rectangles should be, because the width is actually already determined. The width is 1. So the width is this piece right here. We just need to find the height of the rectangles. So first of all, let's actually just draw in the rectangles here. Let me do that in a different color. How about blue? So I'm going to first of all look at this interval right here between 0 and 1. So it says between 0 and 1, the other key piece of information that we have, we want to use the left endpoints for the height of each rectangle. This is really important. So between 0 and 1 on this subinterval right here, 0 is the left-hand endpoint. So I'm going to look at the height of my function at 0, which is right here, and I'm going to draw in a rectangle that is that tall and this wide. So is, in this case, 9 units tall and 1 unit wide. And here my rectangle looks something like this. We'll come back and worry about the area in just a moment. But here, this is just a good start. Here I just want to draw in the rectangles just to get an idea of what we're doing. And then I'd say, okay, well that's a pretty good approximation. Now I'm going to move on to the subinterval 1 to 2. And again, keeping in mind we're using left endpoints here. So I'm going to use the left endpoint 1. So the left endpoint of 1 right here, that will determine the height of my next rectangle over that interval from 1 to 2. And there's my rectangle. Let's see if I can draw that in a little bit better. There we go. There's my rectangle. And then lastly, the subinterval between 2 and 3. I want to look at 2. That's the left-hand endpoint for that subinterval. So I'll look at what's the height of my function at 2. And there is my rectangle. Now, obviously, if you were to look at this, well, let me explain what we're going to do first. We're going to find the area of each one of these rectangles. So that rectangle, we're going to find the area of this rectangle, and then we're going to find the area of this rectangle. And we're going to add them up. And we'll use that as an approximation for the area under the curve. Remember, this piece right here that I'm highlighting in now, this is what we're trying to find. But there are some problems. There's a reason I'm saying that this is an approximation. It's because each one of these rectangles has this little area that I'm going to find that's above my function. That's too much. So hold on to that idea for right now. I just want to point out right now that this is not a very good approximation. But we have to start somewhere. So let's break this down into 3 parts here. I'm going to call this first rectangle the leftmost rectangle. I'm going to call that rectangle 1. So if I want to find the area of rectangle 1, and actually let's just think about the area of a rectangle is given by length times width. The width we said was delta x, which is just 1. The length, or the height, if you want to think about it that way, that's how tall each one of these rectangles is. And that is going to be determined by our function. Remember that this black function here that I've drawn in right here, this is f of x. This function right here is f of x equals 9 minus x squared. And we used the left endpoint of each interval to determine the height of, or the length of the rectangle. So I'm going to take some number in each subinterval, and we'll talk about which one, and plug that into our function. I'm going to call this f of x star. And we'll say f of x star. So we're going to take some number, plug it into our function right here, and then multiply it by delta x, which is 1. So if I want to find the area of that first rectangle, so if I want to look at the area of rectangle 1. So here in this case, I'm going to think about it this way, f of, now we said we were using the left endpoints for the height of each rectangle, or the length of each rectangle, whichever word you want to use. So we used 0 to determine how tall this rectangle should be. That was this length right here. So this one we could actually count since it's right on our y-axis. But let's say my graph is not particularly great. I actually think my graph is pretty good, thank you. But let's say you don't really trust your graph. We can always verify the y value by taking that left endpoint, again, only because we're using left endpoints. We could very well be using right endpoints as well. But we're going to take that left endpoint, which in this case is 0, and plug that into our function. So f of 0 times our delta x. So f of 0, remember f of x, that's just 9 minus x squared. So I have 9 minus 0 squared times delta x, that's just 1. So I have 9 times 1, which is 9. So there's the area of the first rectangle. And I'm going to repeat this process 2 more times then. Now I need to find the area of rectangle 2. So the area of rectangle 2, again, is just length times width. So if I want to talk about rectangle 2, so in this case, we were looking at the interval between 1 and 2. We used the left endpoint, so we used the height of my function at 1 to determine the height of the rectangle. So we're going to take 1 and plug that into our function and multiply that by our delta x. Our delta x is never going to change, by the way, so if you just want to plug 1 in for this right away, then that's fine. F of 1, though, that's 9 minus 1 squared times 1. So in this case, I've got 8 times 1, which gives me 8. Lastly, I'm going to find the area of that last rectangle. How about I call this rectangle 3? And there we were on this smaller subinterval between 2 and 3. We used 2 as the height of our rectangle. So I'm going to take, for rectangle 3, I'm going to take 2 and plug that into my function. Multiply that by delta x. So this is 9 minus 2 squared times my delta x is 1. This is, 9 minus 2 squared, that would be 5 times 1 gives me 5. So just to recap what we've done here, I found the area of each one of these rectangles. So there's the first, there's the second, and there's the third. Well, if I want to approximate the area under this curve, I'm just going to take those areas that I found and add them all up. So I'm going to take the areas that I found. So I'm going to take 9 plus 8 plus 5. Let's see, 9 plus 8, that would give me 17 plus 5. My approximation is 22. So 22 square units is my approximation for area under the curve. Now, this is an approximation. I know that this is wrong because we said, hey, there's this little piece in each one of these sections that there's like this little bit of overhang, right? Each one of the rectangles is just a little bit too big. So a question that I will often ask is this estimate, is this an overestimate or is this an underestimate? Meaning this 22 units squared, is this higher than the actual value, higher than the actual area under the curve, or lower? In this case, I can look at the area under the curve, or these overhangs, right? Each one of these areas we said was a little bit too big. This is an overestimate here, an overestimate. Because we have each one of these rectangles is a little bit too big, right? This kind of black shaded area that I'm trying to draw in here, that is area that I am counting, that I am including in that 22 units squared, and I really don't want to. It's too much. So this is an example of something called a Riemann sum. I will not be asking you to do Riemann sums, but I will ask you questions about Riemann sums. So for example, I will give you the picture of a function and I will draw in the rectangles, and then I will say, hey, for this approximation, is this an overestimate or is this an underestimate? And you need to be able to tell me. So what an underestimate would look like, I want to draw that in just so that we can see an example real quick. If we worked, let's say the same function, so 1, 2, 3, and let's say we intersected up here at 9. So we still have the same subinterval, so we're still working from 0 to 1, 1 to 2, 2 to 3. If I used the right endpoints in this case, and let me draw those in a different color. If I did the right endpoints and drew in my rectangles, there's one, there's one, and then one more. Actually, this one's kind of weird because this one actually doesn't have a height. This is what my approximation would be for using right endpoints. And look at the rectangles. You want to determine, are the rectangles too big or are they too small? Here the rectangles, let me actually shade this in, are a little bit too small. There's this extra shaded region. Here I'm not counting anything at all. It's kind of goofy. But here, each one of those rectangles is just not quite big enough to cover the area under that curve. So this is an example of, oops, here, let's do this. Let's section this off so that we don't get confused. This is an example of an underestimate. One other thing that I would like to mention here is that it is not necessarily the case that a left sum will always give you an overestimate and a right sum will always give you an underestimate. You need to look at the picture of your graph to determine, do we have an overestimate or an underestimate? If you just look at left or right, you'll be right 50% of the time, right? So it's no better than guessing. You need to look at the picture of your function before you can conclude whether it's an overestimate or an underestimate. So this is kind of cool. It seems complex. There's a lot of steps to it. It's a long process. But at the end of the day, I want you to remember what we're doing. We just found the area of 3 rectangles in this case. We found the area of 3 rectangles and we added them all up. That's all we did. So it's a complex and kind of a long and kind of a tedious process for something that you can actually boil down to be actually fairly simple. But I'll be honest, this approximation is bad. It's not very good. So now we want to think about, okay, how could we improve this approximation? And I'm going to go up here to erase this to draw in and kind of show what's happening here. So if I were to draw in here, let's work with that same function. Let's say 1, 2, 3. Let's say up here, here's 9. My function looks perhaps something like that. We used 3 rectangles, so our sum looked, let's use the left endpoints here. Our 3 rectangles looked something like this. We said each one of those rectangles is a little bit too big. We've got this area and this area and this area. That's too big. So I say, well, what if we didn't have to just use n equals 3 rectangles? What if we used more than that? So instead of using 3 rectangles, I'm going to try doubling the number of rectangles. I'm going to use 6 rectangles. So this time, each rectangle needs to be half as big. So if I look at, and actually, trying to think how I want to do this. No, let's, here. Let's do the original rectangles in blue, because I want to be able to compare these. And then we'll draw new rectangles in red. So if I were to draw new rectangles in red, it would look something like this. I'm covering the same interval, 0 to 3. I'm just cutting it up into smaller pieces. And what I end up with this time is when I look at the red rectangles, it might be a little bit hard to see. There's kind of a lot going on here. But in each one of these sections, there's a little bit of area that I was counting the first time around I'm now not counting it. I've taken my approximation and I've made it better. So we can see right here, and I'm going to try and circle these as best I can. Here I have this little area that I was overcounting before, but in my second guess, my second approximation, when I use twice as many rectangles, I'm now no longer counting that piece. Same thing with this right here. That's a piece that I was counting before. We said our estimate was too much. We're basically getting rid of this piece right here and this piece right here. And then we say, okay, we're going to get rid of this piece right here. It's still not perfect, but it's definitely better. Each one of these rectangles is still a little bit too big, but the overall area that kind of by how much I'm too big, how much I'm overestimating is a little bit better. I've gotten closer to what I think the actual area is. And there's nothing particularly special about doubling. I just chose it because it's easy to draw in there. If we had just chosen, say, if we chosen to use 4 rectangles, our approximation would have been better. So hopefully you have an idea of where we're going here with this. In order to get a better approximation, we need to use more rectangles. This is something that I really want you to take home. This is a question that I will ask you about. So if we have an approximation, we can always improve it by using more rectangles. Take that approximation, add more rectangles to it, use the same interval, so we're still working on the interval 0 to 3. But if we go, say, from n equals 3 rectangles to n equals 6 rectangles, we're going to have a better approximation. So this means that more rectangles gives us a more accurate approximation. The problem here is that any finite number of rectangles will still have some error. This is kind of similar to the endpoints discussion that we had, where even if it looks like it's perfect, you can still kind of zoom in infinitely and get closer and closer, no matter how small you cut up your intervals. You're always going to be able to zoom in and see just a little bit of error. So if any finite number of rectangles gives us some error, then we will need an infinite number of rectangles for a perfect estimate. So here's how I'm going to find the area under the curve, and this is also how we define the definite integral. So first of all, the definite integral of f of x over a to b is denoted as this. So it looks a lot like the indefinite integral. The new parts really are these limits of integration, a and b. A is called, this piece right here, a is called the lower limit of integration. B is called the upper limit of integration. And this is so cool because this will tell me area under the curve. This answers a really, really big question. And it turns out the way that this is defined is it's defined like this. So if you look at this, you got this really complicated looking thing right here. I'm going to try and break it down. So when we said f of x sub I times delta x right here, this is really length times width. So hopefully you see that length times width similar to what we were doing up here. Length times width, that's just the area of our rectangle. This piece right here says, okay, you're going to take all n of your rectangles, so whatever n is, so in our problem n was 3. You're going to take all 3 of your rectangles, add them all up. It's called sigma notation. But you're going to take all your areas and add them together. But then we said, oh no finite number is going to work here. We need an infinite number. So we're going to look at this n right here. That's where we would stop. We're going to say, well, we're going to look at the limit as that number n, the number of rectangles we use, approaches infinity. So what we're really looking at is we're looking at, okay, if we were to use an infinite number of rectangles, that would give me a perfect approximation, and that would tell me area under the curve. So this is really, really cool. It's a really powerful theorem. It says if you look at this, the definite integral from a to b of f of x dx, this tells us net area under a curve. And more on this word net area here. For now, don't worry too much about it, but we'll talk more about that in later videos. So cool, I know how to find the area under the curve. I just have to evaluate this definite integral. Great, how do I do that? Well, we have to, of course, use something called the fundamental theorem of calculus, which, guys, I'm going to have to end this on a cliffhanger. I'm sorry, but go take a look at the next video if you just are so excited and can't wait. We're going to learn how to evaluate definite integrals, and that will also tell us how to find net area under curves, which is a pretty big deal.